We're going to be working on problems today dealing with Planck's constant and the fact that an electron can act like a particle and it can act like a wave. So the wave-like properties of the electron deal with two equations. And the first equation actually goes with all waves, and this deals with the fact that the electromagnetic spectrum, which is everything from a radio wave clear through to a gamma wave, will travel at the speed of light in a vacuum. So this c is a specific c. It's not just the speed of any old wave, it's the speed of an electromagnetic wave, which always travels at 3 × 10⁸ meters per second in a vacuum. And that's the number that we'll use. That number won't always be given in the problem. You're just going to have to know that if it says that the speed of light is traveling, that's going to be the speed of light. The other two variables that are in this equation are weird. They're from the Greek alphabet. This is a lowercase lambda. I think it looks like a lowercase y just flipped and upside down. So that's the wavelength, and it has to be measured in meters. And then this weird looking V is called a nu, and it's a lowercase nu, and it looks like a V with kind of like a warped top or kind of slanted or something. That stands for the frequency of the wave, which is the number of cycles per second. And instead of saying cycles per second all the time, we use the frequency of a hertz, which is a man who actually worked with waves a lot, and so they made a cycle per second, the unit for frequency, equal to his last name, which is a hertz. It's an H and a Z. So that's the first equation that we're going to use. And then the second equation comes from Planck's constant. Planck figured out that for certain materials, if you would shine certain amounts of energy on them, they would produce certain colors. And so he said that the frequency of light, or the frequency of the electromagnetic spectrum, is directly related to the energy of the wave. And so his constant, this Planck's constant, is always 6.626 × 10⁻34. And then this is a joules second. Energy is measured in joules. That's what the E stands for. E is the amount of energy that the particle has, and it's going to be measured in joules, and then that's the frequency, the same frequency that we had over here. Now because of that, because you have two equations that share a similar variable, this second equation, when you substitute in, can also be equal to that. I took the first equation and I rearranged it and solved it for the frequency, and then I plugged the frequency into this equation. So the amount of energy that a photon of light or a quanta of energy from an electron can have is equal to Planck's constant times the speed of light. Both of these are constants divided by the wavelength, which has to be measured in meters. So this is like a third equation that you can add to the equations in this chapter. And so I'm going to do a couple of sample problems dealing with both of these, and then you'll have some to practice on your own from the book. So the first sample problem is on page 140, if you have that scanned or are able to look at that. And it says that microwaves are used to cook food and transmit information. What's the wavelength of a microwave that has a frequency of 3.44 × 10⁹ hertz? So they've only given you one number in that particular problem, and they've told you that it's the frequency. So you have to know that the frequency is that weird looking symbol, the nu, and it's equal to 3.44 × 10⁹ hertz. And they want to know what the wavelength is. And that's all the information that they give you. And this is where you have to remember that the speed of light is a constant, 3 × 10⁸ meters per second. And so you have these two variables, and you're looking for that one. So that means you're going to use the first equation. The speed of light is equal to the product of the wavelength and the frequency. This is the variable that you're looking for, so you have to rearrange the equation a little bit by dividing both sides by the frequency. And so then you're going to have the wavelength is equal to 3 × 10⁸ meters per second divided by the frequency is 3.44 × 10⁻meters, cycles per second. That's what a hertz is. And then the per seconds are going to cancel out, and that's going to leave you with meters. So you're going to take 3 × 10⁸ and divide it by 3.44 × 10⁹, and you're going to have to remember to have significant digits, so I'm allowed to have 3, and it's going to be 0.0872, and that's going to be meters because that's the unit that's left. So that's how we work with the first equation. You're given two of the variables. One of them will probably not be given in the problem. You're just going to have to know the speed of light is 3 × 10⁸, and then you're going to be asked for the other variable. The second equation is used pretty much the same way. There's a sample problem in your book, or if you scanned it, on page 143. And this is to find the energy of the photon. So when you see something that talks about energy, this is where you're going to use the second equation or the variation of the second equation. So it says every object gets its color by reflecting a certain portion of incident light. The color is determined by the wavelength of the reflected photons, thus by their energy. What's the energy of a photon from the violet portion of the sun's light if it has a frequency of 7.23 times 10 to the 14th, and that's going to be hertz, or cycles per second. So they want to know the amount of energy that a photon has, and it's violet light. And they're saying that the the frequency of the light is 7.230 times 10 to the 14th, and this is hertz, or cycles per second. And that's all they give you. So what you have to remember is there's another constant, and that's going to be Planck's constant. So you're going to use the equation as is. The Planck's constant times the frequency is equal to the amount of energy that photon has. So this is going to be 6.626 times 10 to the negative 34th joule seconds. You're going to multiply that by the frequency that was given in the problem, 7.230 times 10 to the 14th. And then you need to remember that a hertz is, sometimes they write it as like this, a per second, or you can think of it as per seconds like that because it's a cycle per second. So I'm just going to put seconds to the -1 or per second. When I multiply these two things together, I have 4 significant digits here and 4 significant digits here. So I'm allowed to have 4 significant digits in my answer. I'm going to have 4.791 times 10 to the -19th. And then this second here will be canceled out by that second there, and you're left with joules, which is good because that's what energy is measured in the metric system. So that's how you use the two equations. Sometimes you can use this equation as well to figure out the amount of energy, but basically this is how they're done. You have to rearrange very simple algebraic equations.